Good morning, everyone. Welcome to another Math Club talk. Today, the topic of the talk is analytic continuation of the zeta function and prime number theorem. The talk is given by Amit Kumar Basistha. He is a student in the second year in B Math. Over to you.
Thank you. Before going into analytic continuation of zeta function and prime number theorem, I would like to introduce some basic notions in complex analysis. So, in complex analysis, first we want to go to differentiation. So, in complex, a differentiable function is called a holomorphic function. So, the definition is quite simple. It is holomorphic at z equal to z naught if this limit exists. But note that this notion of differentiation is quite strong in the sense that this limit should exist through every path that reaches z naught. So you should reach z naught not only from this direction and this direction. You should be able to get a value of the limit no matter how you approach that point. And this notion is strong in the sense that if a function is holomorphic, you can prove that it is not only differentiable once, it is differentiable infinitely many times, and it also have a Taylor series expansion. So if it is differentiable at a open set, then you will have many nice enough properties, and those properties will be used later on. So one of those properties is, which will need, like, it's called the Cauchy's theorem. It says that if you have a holomorphic function and a closed curve in an open set, so you have an open set where you have a closed curve and function is holomorphic in this open set. So if you integrate the function over this curve, this integral is 0. So this is called the Cauchy's theorem. We will be needing this theorem later. Also, I want to go a little bit into singularities. So singularities of a function. So a point z naught is called a singularity of a function if the function is well defined in a neighborhood around z naught, but it is not defined in z naught. So these are called singularities, and there are three types of singularities. One is called the removable singularity. So removable singularities are like functions of this form. Say, in a sense it is not defined at z naught, but you can easily make it defined at z naught. So these are like, you can redefine the function at that point so that the function becomes holomorphic at that point. So these are called removable singularities. The second type of singularity is poles. So at poles, what happens is the function is not defined at that point, and 1 by f is also not defined at that point. But if you define 1 by f to be 0 at that point, 1 by f becomes holomorphic. So it is like a 0 of the function 1 by f. So poles are like something of this form. Say it has a pole at 0. You can define 1 by f to be 0 and it becomes holomorphic around that point. And the third type is essential singularities. We won't go into this, but these are anything that are not removable and poles, and these have really crazy behavior, and we won't need this type of singularities. Mostly our focus will be on poles of functions. So one nice thing about poles is we saw Cauchy's theorem that if it is holomorphic in an open set, the integral is 0. So what happens when there is a pole? So you have a curve, it is holomorphic here except at a point where it has a pole. Now one thing about pole is, okay, I should say this thing. So a function is 0, then it can be written like this. It is holomorphic and it has 0, then it can be written like this. Gz doesn't vanish around z naught, and so this is called the order of the 0. So if it is 0 of order 1, it will have a factor of z minus z naught to z naught, and some function which doesn't vanish at the point z naught. So a function which is not identically 0 and is holomorphic and has a 0 at z naught can be written in this form, and this is called the order. Similarly, if a function has a pole, it can be written like this, where Gz is holomorphic around z naught, and this is called the order of the pole. So it is just analog of the 0. and what happens is it is holomorphic, so it will have a Taylor series expansion. So you can write it like this. It will have a Taylor series expansion. You multiply these two. This means you will get an expansion of this form. Right. Here the coefficient of z minus z naught to the power minus 1, which is a minus 1, we are denoting by a minus 1, is called the residue of this function at the point z naught. So residue of f at z naught is a minus 1. So what happens when you integrate a function which is holomorphic in an open set? So you are integrating along a curve, and inside the curve it has only one pole. So this is the curve say C. You scale by a factor of 1 by 2 pi I. You just get the residue of the function at that pole. And if you have multiple poles, you will get the sum of the residues at all these poles. So poles in C. This notion is useful, and another notion like sometimes instead of looking at the function, looking at the logarithmic derivative of the function is helpful. So this is called the logarithmic derivative. You are just taking the log of the function and differentiating it. So what happens when you suppose a function has poles and zeros in this curve? It doesn't vanish in the boundary of the curve. It doesn't have pole in the boundary of the curve. It has some poles and some zeros inside the curve. So what happens about the what can you conclude about the poles and zeros of this? So if you write poles and zeros in this form and differentiate it, you can notice that it has simple poles only at the points where f is either 0 or f has a pole. So by the way, by a simple pole I mean a pole where n is equal to 1. These are called simple poles. So this function has a pole, simple pole, when f is either 0 or f has a pole, and the residue when f has a 0 is 1, and when f has a pole, the ratio of this is minus 1. You can just see it easily using the Taylor series expansion. Just differentiate it and then just cancel the terms and you will have that result. So this gives this thing. We will need this later on. Which one? So you are so do you know line integrals and stuff like that? Okay. Yeah, you are integrating along the boundary. So you take a parameterization of this curve. So this is C. Alpha of t is a parameterization of the curve. So it is just this. And you just take the real part of the function plus I times the complex part of the function, imaginary part of the function, integrate the real part separately, imaginary part separately, and then combine them. This gives number of zeros minus number of poles, because it has, when it is 0 the residue is 1, when it is pole the residue is minus 1. So this integral gives the number of zeros minus the number of poles. So these will be some notions that will be helpful and we will need later on. Okay, so I will define one last notion, meromorphic functions. So meromorphic functions are something close to holomorphic. So a function is meromorphic if it is if there exists set of points which doesn't have limit points. So the function is defined on a open set omega. It doesn't have a limit point. In this set, this is S. So this set S doesn't have any limit point in omega. Sorry. This set S doesn't have a limit point in omega. So a function is called meromorphic if there is such a set such that it is holomorphic in this and it has poles in here. So it is holomorphic here and it has poles in here. And the reason for not allowing limit points is, see, once you have a function which is holomorphic, the roots of that function cannot have limit points. That is something I think done in real analysis 2 also. So a analytic function cannot have limit, the zeros of analytic function cannot have limit points. So if it is holomorphic, if the poles have limit points, if you take 1 by f, the zeros of 1 by f will have limit points. So f has to be identically 0, which 1 by f will be identically 0, which means f will be infinity everywhere, which doesn't make sense. So that's why we don't allow limit points in this set. So it is called meromorphic if there exists such a set. It is holomorphic here and poles here. So meromorphic function will be quite useful for us because what we want to do is, we know these functions. There are well-known functions like zeta function, gamma function. So we don't want to study them in their usual domain. Suppose we have the zeta function defined like this. This thing is well defined only here. This definition works only here. So we want to find alternate definitions which agree with this definition at this point, at this domain real s bigger than 1, but it can be defined in the entire complex plane. And if we can't, we will try to define in some part of the complex plane at least. At least we want to extend this domain and study the function in a larger domain. So for that, first we will go into gamma function, because essentially the analytic continuation of the zeta function comes from the continuation of the gamma function. So the gamma function is defined like this. This is the gamma function, and this is well defined for this. Now we want to, so this is the theorem, analytic continuation of gamma function. So this is something we will do a lot, that sometimes the more than the definition of the function, some properties of the function become more important. Like we define the analytic continuation based on some property. So one of the well-known properties of gamma function is this. So we want a function that actually preserves this thing. So what we do is, for s between -1 and 0, we define gamma s to be this. So when s is between -1 and 0, this thing will be between 0 and 1. So this is well defined. And since there is we are excluding this point because at s equal to 0 this will not be defined, s equal to 0, and at s equal to -1 this is not, gamma of 0 is not well defined. So this is how we extend the gamma function. So here you can do something like this. You just go on, once you have done this you can inductively go on. Right, once you have defined it -1 and 0, you can define -2 and -1. And so this gives an analytic continuation of the gamma function in the complex plane, except at this point 0, -1, -1. And you can show actually that it has poles at these points. So this is a meromorphic function which has poles at 0, -1, -2. So this is the analytic continuation of the gamma function. So this is pretty easy to derive. They are actually simple poles. Actually you can see also, because what happens is between -m less than s less than 0, you can define it something like this, right? M s plus 1 . So see, except at s, so there is a n between m -m and 0. So only the thing s plus n will vanish. The others are well defined. So you just pull it out and see the residue. And the residue is actually this residue at n. Residue at -n. Sorry. Yeah. Sorry. That's my bad. Because here also this is real part of s bigger than 0. Once you have real part of s bigger than 0, this thing will automatically become well defined. So zeta function this one. So using, you can actually show, this is easy to show, it's just basic, you can bound this and then show convergence. It's the same as real case. You just take the modulus, then use triangle inequality to bring modulus inside. So you can show that this is well defined for this real part of s bigger than 1, because once you take the modulus, it just becomes the real part. You can show that, that's not difficult to show. So this is well defined for a real part of s bigger than 1. And one thing is, zeta of s is holomorphic. So this is not obvious at all, but again, holomorphicity has a really strong implications. So one thing which is very different from real analysis, if you have a sequence of functions, series of functions converging to a function set. For real, it doesn't hold that derivative of the sum is equal to sum of the derivative. But once you have complex differentiation, actually you can pull the differentiation out. So that's why, see, these functions are all differentiable 1 by n to the power s. So once you have these are differentiation, the zeta function automatically becomes differentiable, because this is just a sequence of functions converging, uniformly converging to another function. So another thing, right? So I want to define the theta function first, because we will need it now. The theta function is defined to be got it right? Yeah, this is correct. So this is the theta function, and we'll need another important functional equation of the theta function, which is given like this. This is a functional equation that the theta function satisfies. So this thing is actually not at all trivial to get. So I'll just say how to derive it. I am not gonna derive it, because no, you have to just evaluate some integrals and stuff like that. So it actually follows from the Poisson summation formula. So if you have a function and if you have the Fourier transform of the function, the Poisson summation formula says this, right? This is something that the function and the Fourier transform satisfies. So once you plug in this in terms of f, you will get theta function on one side and you will get this thing on the other side. So this is just the Poisson summation formula. This is just the implication of that. So once you have this, see what we want to do is analytically continue zeta function. So what, as I said, sometimes more than the function's definition, some properties of the function become more important. So this is one of the properties of the function, zeta function, that relates it to the gamma function. So first, this property holds for real part of s bigger than 1, because zeta is now, for now it is defined for real part of s bigger than 1. And this is not difficult to prove, because what is theta of u minus 1 by 2? This is just summation n equal to minus infinity to infinity e to the power minus pi n square u minus 1 by 2. At u equal to 1, it is 1. So you can just write this thing as 2 times e to the power minus pi n square u n equal to 1 to infinity. Because when n is negative, this n square, the negative and positive n square, you can combine. Now 2 and 2 just goes out and you have this. So instead of this, you can, this integral you can write it like this. Once again, uniform convergence, take some outside, take this substitution, pi n square u equal to t. The inner integral will become the gamma integral, with some these scaling factors will come out. So it becomes just the gamma integral. You can see, sort of see it, because it will become, what is it, t to the power s minus 1. So it will become t to the power s by 2 minus 1. This thing, there is a e factor, e to the power minus t, and this thing will come out as scaling factors. So this is not difficult to see. So what happens is, you now define a new function to be this thing. This thing. So this function, so what happens is, it is now defined for Re as bigger than 1. But what happens is, this is the theorem, the xi function has analytic continuation to c minus 0 1. It has poles at 0 1, simple poles, and it satisfies this thing. So this is also not difficult. You have, so I will call psi of u to be theta of u minus 1 by 2. So it will be psi of u du. So you have this thing, and you just break the integral. That's integral 1 to infinity this thing. What happens is now you use the functional equation for the theta function. You have theta of u equal to u to the power minus half theta of 1 by u. So you just plug in there that thing here and you take the substitution 1 by u goes to u. So what we want to do is we want to convert this integral from 0 to 1 to 1 to infinity. Because notice this, what is psi u? It is theta u minus 1 by 2. So it is a summation n equal to 1 to infinity e to the power minus pi n square u. So when u is bigger than 1, you can write something like this. Why? Because u is bigger than 1. So when anything that is larger, that will be smaller. So this inequality is obvious. Now this is geometric series. View is this, n equal to minus infinity 2. You subtract 1, 0 goes out, then everything pairs up, divide by 2. That is psi. So this is geometric series. So it will be some constant multiple of e to the power minus pi n, right? Because that series converges, 1 e to the power minus pi, that series converges, it will be some constant multiple of this. So this thing converges for u bigger than equal to 1. So this integral is well defined for u bigger than equal to 1. So you want to convert this integral to 1 to infinity. So for that you use this thing, and once you take the substitution, I will not evaluate the integrals, I will just give the final form what you get. The final form you get is so this is the one from here, and here after taking substitution you get this one times psi of u. So this is the final form you get. Yeah. After you take all the substitutions, you get this form. Now look at this. See, this has exponential decay for 1 to infinity. So this thing, it will dominate this thing, and this thing will be well defined and it will converge. So this will define a holomorphic function. The only problems are here at s equal to 1 and s equal to 2, and those are covered here. They are poles at 0 and 1, and yeah, and one can easily verify. Just plug in 1 minus s, you will get the same expression. This thing will become this thing, this thing will become this thing, and this two will also remain same. So that's the thing. Now once you have an analytic continuation with xi function, you define zeta function to be just versus writing the same expression again and again. You define gamma function, zeta function to be this. See, gamma has problems. Gamma is not well defined in say 0, minus 1, minus 2. But 1 by gamma doesn't have any problem. So 1 by gamma is well defined. It is well defined everywhere. You can prove actually gamma function satisfies this property. So this immediately gives you that gamma has no zeros. So which gives you that 1 by gamma is well defined. It has zeros at 0, minus 1, minus 2. So gamma s by 2 will have 0 at minus 2, minus 4, and so on. Now what happens is, wait. There is a circular definition. So here, so what happens is this is poles at 0 and 1. What happened to the pole at 0? So you write the Taylor expansion, this pole at 0 and the 0 of the 1 by gamma at 0, they cancel out. They are a simple poles. It is also simple pole, it is also simple pole. So you just write the Taylor expansion, it will cancel out. So it is well defined even at 0. The only problem is 1, and it has a simple pole at 1. Otherwise it is well defined everywhere and it is holomorphic everywhere. So this function, this expression of the zeta function is holomorphic and has a simple pole at 1, and it has zeros in this. So once the 0 and pole cancel out, zeta function will not have 0 at here, so it will have 0 only at there. So this gives, so zeta function is well defined everywhere, and this, and we have this identity, right? So this gives, so once you plug in here, you will get something, a identity of the zeta function also. So I'll just write down that identity. You just plug in that expression. So this gives zeta of s just plug in 1 minus s, write zeta of 1 minus s as xi of 1 minus s xi of s, and then just compare terms and you will get this one. So what this identity gives is zeta of s, if it has zeros in this region less than 0, which are not here, just which are not zeros of this thing. So the zeros which are not of this must also be 0 of 1 minus s, right? Which are zeros, which are not zeros of this are also zeros of 1 minus s. So what happens is, for real part of s less than 0, what you can prove is, if this doesn't have 0, this also doesn't have 0. So the only zeros except this, except in this region, are this -2, -4. I have not gone into the details of that proof, but it is not difficult to see. We just exploit the symmetry and then just calculate some stuff and use the series expansion. Once you have that real part of s bigger than 1, you can use the normal summation 1 by n to the power s. So using that, you can arrive at this conclusion. Also, this gives a nice insight into how Riemann came into the Riemann hypothesis, because see, it is symmetric about, somewhat symmetric about 1, right? So in this region, it is somehow natural to expect it is in this line half, because once you plug in half here, this thing will also become half. But once you, otherwise there should be, the zeros must be symmetric somehow. So it is 0, 1. So suppose it has something here, it must also have something here. So it is, so that's give a sort of an idea, you know, this is the point of symmetry. Half is just the point of symmetry. So this is one of the just basic intuitions. But anyway, I don't think I can prove this in this lecture, but still. What else? Okay. So I want to prove one important property. So we had, it has a simple pole at s equal to 1. It doesn't have any root. So we have characterized all root outside this interval, right? So one important fact which we use in our proof is, of the prime number theorem, is, if you have this line, real part of s equal to 1, we want to conclude that there are no roots in this line. And this is actually, people say this is one of, so if you go at Professor B. Suri's homepage, there is one line written that the prime number theorem has a one line proof. The zeta function doesn't vanish in this line s equal to 1, real part of s equal to 1. So this was one of the things that Riemann couldn't prove, and people say that if Riemann had this result, he himself could have proved the prime number theorem. So this has serious implications in the prime number theorem. So, and the proof of this result that I have is really uninspiring. I don't know how you come up with that one, but I'm just gonna give the proof. So suppose it has a root at this point 1 plus I t naught. We are assuming there is no root. Suppose it has a root, we will contradict this. So look at this thing. You can bound this by this as sigma goes to 1, means sigma is close to 1. It has root, so it must have root of order at least 1, because root cannot have right fraction order or something like that. So you can bound it like this thing actually. Sigma goes to 1 plus we'll go from positive direction anyway. Now it has a root, it has a pole at simple pole at here, so you can write it like this, some constant time, some constant time minus 1, and this is because it has simple pole. Because it has pole of order 2, then it will be minus 2 and something like that. And it is, look at this point, it is holomorphic in this point, so it will be bounded near this point. Some b, right? Now you consider this thing. Whole to the power 4 zeta of sigma whole cube of sigma plus 2 I t naught, this thing. So this finishes at least to the order 1, because this will become to the power 4, this will become minus 3, and this will be bounded. So this thing will become to the power 1, this thing will become, this is bounded anyway. So this goes to 0 as sigma goes to 1. So we want to contradict this, because we want to say that there is no 0 here. So what we do is say call this quantity t, this is a real number, right? So what will show that log of t is always positive. So t is going to 0, near 0 logarithm will take negative values. So if log of t is always positive, for whatever sigma you pick, you are done, because this thing cannot go to 0 in that case. So that's what will contradict. So what is log of t? So for that we'll need how log of zeta function looks like, right? And taking logarithm of functions, this is a bit tricky, but for those who know, so if you have a function that is holomorphic and doesn't vanish in a simply connected domain, so those who don't know the definition don't bother about it. But if it doesn't vanish in a simply connected domain, then you can define logarithm of function in that domain. So essentially you construct a path and then you do some integral to define the domain, define the logarithm. So log of zeta is well defined for real part of s bigger than 1. We will consider real part of s bigger than 1 because we are approaching 1 from the positive. So here we can write zeta function like this, right? Where is just the analytic continuation? It should agree with this function at this domain, in this domain. So I think most people know this, but I'll just product over primes. Do everyone here know this all-time formulation, or should I? Everybody knows this, right? Okay. So this is just this, because you just you just look at the denominators and stuff like that. This is just the infinite series 1 plus 1 by p plus 1. So you like it, write it in terms of the product. So product becomes sum. You write the Taylor series expansion of log. E to the power minus m right? Now you define Cn 1 by n 1 by m. So notice this thing. See what happens is when n is a power of a prime, Cn will become 1 by n, and this will become p to the minus ms. So this will just agree with this thing. When it is not a power of prime, this will become 0. So it will not even appear here. So this thing becomes this thing. Now you want to, so yeah. Now what is mod of the logarithm? We need mod of log, right? So mod of log of z, say. So you have z equal to r e to the power I theta. This is just log r. Say mod of log z, sorry, log of mod z plus I something I theta plus, sometimes to make it well defined you need some times some 2 pi something factor, but we will not go into those things, but this is just for making it well defined. So there are some continuity things coming up, but whatever, there is some I factor. What is this? Log of mod z plus I something. What is this? So this is just real part of log of z, log of mod z, right? So what expression did we have? We had this expression. I shouldn't have raised it. We had this expression. We want to take log. What happens when we take log? Log of t is just 4 times log of mod zeta sigma plus I t naught plus 3 times log mod zeta sigma plus log of zeta sigma plus 2 I t naught. You just take log of t. Now this is just real part. So you can replace it by real part. Now we have an expression for log of zeta, right? What is the real part of this expression? This thing is a real number, so it will remain Cn. What is real part of n to the power minus s? So s equal to sigma plus it. So n to the power minus s is just e to the power minus s log n. Just e to the power log n is n. Wait, I will write it nicely here. So n to the power minus s is e to the power minus s log n. This is e to the power minus s. S is sigma plus it log n. This will become e to the power minus sigma log n, e to the power minus it log n. This is just n to the power minus sigma. And what is the real part of this? Real part is just cos of t log n. This is just the real part. So real part of n to the power s is n to the power minus sigma cos of t log n. So 4 times real part. So once you have that, what we have 4 times n to the power minus sigma cos of t naught log n plus 3 times n to the power minus, oh, there is cn here minus sigma cos of, for the second here t is 0, so it will just become n to the power minus sigma cos of 0. This is 3 times, this is 4 times, and n to the power minus sigma cos of 2t log n, and there is summation, there is cn here. So taking everything common, just cos 2 theta you write it as 2 cos square theta minus 1. So what we will get is just summation cn n to the power minus sigma 2 times cos t log n minus 1 whole square. It's just 2 cos square theta minus 1, it will just become it will just break into this formula plus 1. Sorry. So what this shows is log of t is positive because t is a square and cn is always non-negative because cn is either 0 or 1 by m, and n to the power minus sigma is positive. So this shows that t is always non-negative, so which is a contradiction because t is going to 0, a number going to 0, the logarithm must go to negative. So once this is done, I think we can go to, see, we want to prove prime number theorem, but what is the prime number theorem? You have the prime counting function pi x, the number of primes less than equal to x. So you want to prove pi x by x square by 2 goes to 1 as x goes to infinity. This is the prime number theorem. So instead of proving this, we will prove something, some alternate statements. So we define this function. So the von Mongol function first, x square by 2, or x square, sorry, x by log x. I'll say why it is x square by, why x square by 2 arises. Actually we will prove x square by 2 later on. That's the alternate formulation of the prime number theorem. So the von Mongol function lambda of n is this, and we define these functions. This is a Chebyshev function. This is defined to be the partial sum of the von Mongol function. This, and the Chebyshev second function, we define it to be this integral of the Chebyshev's first function. So what we will prove is, if this, then and then so this is, we are not going to prove this, we will prove this because it is easier to manipulate integration. There are expression of this function can be related to the zeta function. So let's see the proof of the first implication. I am not going to give because that is quite obvious. See, if this is growing at x, this should go at x square by 2, right? So this implication is sort of intuitive, and it is also not difficult to prove. You can just take alpha between 0 and 1 and you can just bound it. You take lim sup and lim in. You show lim sup of, if this goes to x square by 2, then lim sup of this must go to, so you have to show that lim sup is less than equal to 1. Lim sup of psi x by x less than equal to 1, and separately you show limit of psi x by x bigger than equal to 1. So this shows that the limit must be 1 because the lim sub is less than equal to lim sub is bigger than equal to lim. So if this is true, then the limit must exist and it should be equal to 1. So you show that, and that's not difficult because it's just partial sum and you can somehow bound it, and it is sort of intuitive also because if it is growing at x, it should grow at x square by 2. What we will prove is this non-obvious direction because this is not at all obvious why you should expect this to happen. So for that you write this. What is psi x? Psi x is just summation n less than equal to x. Here also we will go to lim sub and lim imp. So primes p prime. You just expand von Mangal function because von Mangal function doesn't take any value when it is not a power of prime. So you just want to expand it into a power of prime. Log of p. You fix a prime and then you expand it. Now, how many powers of p are there less than x? It is just floor of log x by log p. Just log x base p. Just floor of that. This is less than equal to summation p log x. You just remove the floor because floor is less than equal to the number. So you just remove the floor. This will cancel this. What is this? Pi x log x. You divide out by x. Take lim imp. Once you take lim imp, everything will go out here. This one. This limit exists. So lim imp will also go to 1. We are assuming this is x. First we are assuming this. This implies this. Now we assume this. So yes, lim imp exists. The limit will also exist. So this limit will become 1. So this shows that lim imp of pi x by log x bigger than equal to 1. Now we have to show the lim sub stuff. So the lim sub one is a little bit more involved. For that you first fix. So you have wait. So is this inequality obvious for people? See, what we have is this. We have this equal to this. Use the x here. We have this, right? There is at least one. So we are just taking one and discarding the higher powers because we are just discarding some positive numbers. This thing is bigger than or equal to this thing. Now, now we are just truncating some numbers towards the end. Now, what is log p? Log p is bigger than log x to the power alpha. Alpha log x. Now, how many primes are there between these two numbers? Just pi x minus pi x to the power alpha. Alpha log x. Right. So you just take it here, pi x by x minus pi x plus pi x to the power alpha by x log x alpha. Just take this thing in this here is bigger than pi x by x log x times alpha. Now we have x to the power alpha is bigger than pi x to the power alpha. So pi x to the power alpha, because number of primes less than x to the power alpha should be, this is just obvious. So since this is bigger than this thing should be also bigger than this. You take x to the power 1 minus alpha. No, alpha minus 1, sorry. So now take lim sup. What happens is this thing goes to 0 because alpha is between 0 and 1. This thing goes to 0. This thing goes to 1. What happens is this sup shows lim sup of pi x by x log x. This is less than equal to 1 by alpha. Now alpha is arbitrary between 0 and 1. So this shows lim sup is less than equal to 1 as alpha is arbitrary between 0 and 1. So what we are going to prove is psi 1 is actually asymptotically x square by 2. We are not going to prove pi x is x by log x, because pi x is something sort of inherently discrete. You want to use complex analysis, you want to just integrate somewhere. So you can't integrate pi x or get some formulation of integrals in terms of the pi x. So psi 1x is defined in terms of an integral. So it is more reasonable to expect that you can get something out of that. So we have only two more theorem, the prime number theorem and so the theorem that relates psi 1 with zeta function. So this is a theorem. So you have real part of c bigger than 1. C is a real number bigger than 1. This means you are integrating along the line real part of c equal to real part of s equal to c. Okay. So we have enough time to. I'll just sketch the proof probably. Yeah, I'll do that. This Simon. Now what is psi of u? Psi of u is just summation of the von Mongol function, right? Now you write this as an infinite sum. So you define fn to be. So you just write it as infinite sum. So you just write it as indicator. In terms of indicator, you write u bigger than equal to n. Summation n belongs to n. This is just a finite sum, so you can take the sum outside. And this is independent of u, so you can take the von Mongol function outside. So what becomes is n belongs to n. Von Mongol function integral 1 to x indicator u bigger than equal to n du. So this is just, what is this integral? Integral n to x, because for u less than n it will just vanish. So what is this? X minus n. Also, if you guys remember the logarithm of the zeta function, log of zeta summation over primes summation over m p to the power minus ms by n. We just took the Taylor series expansion and stuff like that to get arrive at this one. So what is zeta prime by zeta? So if you take derivative, so uniformly convergent, you can take derivative inside p comma m. You are taking derivative with respect to s, so it will become minus will come out, minus m will come out, and log of p will come out. Yeah, m cancels, so it becomes this. So if you take negative here, this negative will go out. You have log p by p to the power minus ms. And what is this? Because see, the von Mongel function becomes log p when p is p to the power m. Otherwise, when n is p to the power m, it will become log p. Otherwise, it will become 0. This function also is. So this is just this thing. So yeah, n less than equal to x. Yeah, n less than equal to x, because here we are taking, yeah, fine. Thanks for that. So what we are doing is, you have this expression for zeta minus zeta prime by zeta. So you just plug it in here. So what happens is, we have this integral. We have this thing. Now, wait, I missed something. We need 1 by 2 pi. It's just a scaling factor, because while evaluating the integral, you are using residue theorem somewhere. That's why 1 by 2 pi factor comes up. So this gamma, this thing lambda and von Mongel function come out, because this is not dependent on s. This thing will come out. Some will come out because of uniform convergence and all that. You take one x out. Now this thing becomes, see, what is this? This is just x by n whole to the power s dx. So you have to just evaluate this integral. Now evaluating this integral, I am not going to go through the whole evaluation of the integral, but the whole idea of evaluating this integral is, you have this thing a to the power s by s into s plus 1. You have to integrate this, evaluate this integral. C minus I infinity, C plus I infinity. 1, this is C. you have this line, you fix t here, t minus it, c plus it. So if a bigger than 1, bigger than or equal to 1, so you take a large enough t such that now you integrate in this region. What is the integral? What is this? It has only poles at 0 and minus 1. Sorry, use not 1. Take t big enough such that it contains both minus 1 and 0. What is the residue at 0? The residue at 0 is 1 by 1, which is 1. What is the residue at minus 1? It is a to the power s by s into s plus 1. The residue at minus 1 is minus 1 by a. Right, residue at minus 1 is minus 1 by a. So when you integrate over this is just 1 minus 1 by a. Now you take t goes to infinity. So what you can do is, I am not going to do the whole calculation, but what you can do is, see, a to the power s. Here s is mostly taking negative values. So what will happen is, integral over this curve will go to 0. Because this thing you can dominate, these are just, this thing you can bound. So the only thing that will remain will integral over this line, and which is this integral. So what we get is 1 minus 1 by a if a bigger than equal to. I think bigger than not equal to. Let me check. It is just okay. It doesn't matter. Doesn't matter. And for a less than equal to 1, I mean it is continuous, so it will not matter. It will become 0 here, and at a equal to 1 also it is 0. So both expressions are valid. So you integrate in this region. So what happens when a is less than 1? This thing will not remain bounded when s goes negative, because a is less than 1, this thing will increase. So you want to integrate in this region. Now there is no pole here, nothing here, so the integral is 0, and this integral goes to 0 this time, because a is less than 1. As increases, this thing will become bounded. So integral over, only thing that will remain was integral over this line, and since the whole integral is 0, this integral will also be 0. 0 less than equal to 1. At 1 the values agree, so don't have an issue. So we just have, this is just summation x. So when this is bigger than equal to 1, so x by n bigger than equal to 1, n less than equal to x. 1 minus x by n. 1 minus 1 by a. 1 by is n by x. So x, take x inside, x minus n. Oh, I erased that one. You remember the expression for psi, right? In terms of the sum. We got this by just expanding the integral and writing the integral as sum. So this integral is this, and this is this. So this gives us the identity, that thing. So we just have, so once we have this identity, we can now go on to the proof of the prime number theorem. So what will exploit is two things. It has no roots at s equal to, real part of s equal to 1. So what that means is, see, the roots doesn't have limit points. It is holomorphic except at s equal to 1. The root doesn't have limit points. That is something, the set of roots doesn't have limit points. That is something we will exploit. And the second thing we will exploit, that is a pole at that point. So one thing for everyone to notice is this thing. This thing has a simple pole at s equal to 1, because what are its poles? Each poles are the poles and zeros of s, zeta. That's what we got at the beginning. For f prime by f, the poles of this, it has simple poles at poles and zeros of f, and the residue is 1 if it is a 0 and minus 1 if it is a pole. So what will be the residue at s equal to 1? It's minus 1, minus 1, minus 1, plus 1. And you have x to the power s plus 1 by s into s plus 1. What is the residue of this? X square by 2. It is holomorphic. So the residue is x square by 2 at s equal to 1. And we want to prove it is x square by 2. So we have to somehow use the pole at s equal to 1 to prove that psi 1x is just. So prime number theorem. So first we have psi 1x is integral along this line. See, s equal to 1. Now we consider a different contour, this one. So for the moment consider this thing, call this fs, call this function fs. So what we want to prove is integral of fs along this line is same as integral of the function along this curve. Suppose call it gamma t, where t is just this one. This is 1 minus it, 1 plus it. This is c minus it, c plus it. So we want to prove this integral is equal to this integral. So for that it is same to prove that this integral minus this integral is 0. So this integral is this, and so first fix t here. Let's first truncate the integral. We will take t goes to infinity. This is minus t, t. This I, put the I in the appropriate places. So you have this contour and you have the other contour. So here you are going like this, and since you are subtracting this, here you are coming like this. Am I doing the right thing? Sorry. Oh, this is not this, right? It is c equal, real part of s equal to c. Sorry. This is s equal to 1. This is this contour, and you have this contour. This line, not that one. Res equal to c. This is c minus it, c plus it. Here you are going in this direction. Here you are coming back in this direction. Now this thing will cancel. Just going and coming back. Here you just make something like this. Here also you make something like this. So what happens? This is a closed curve. This is holomorphic here. This thing will become 0. This integral. This integral will become 0. What will be left is only this integral. Integral is 1 plus it c plus it. Then it is in this direction, and it is in this direction. 1 minus it, c minus it. So if you take the difference of this integral along these two curves, it is just integral along this and this. And you are taking limit t goes to infinity. So, and you have to use a property of the zeta function here. So this is a property of the zeta function. So this is something about the growth of the zeta function. You have this value. You can bound this by actually for any eta bigger than 0, there exists a constant here, and this is not difficult to prove. You just have to write it in terms of series and then just being some bounce in here and there. So this just says that also this obviously s equal to sigma plus I. So what it says that outside this box s equal to 1 you have a bad point. You consider a box here, and outside this box it is behaving nicely. So its growth is pretty small and you can bound that growth. So using this, so you just use this bound and plug in by 2 pi I rel, so 1 plus it to c plus it fs ds. Now you just bound this, take bound inside and use this bound of the zeta function. That will essentially give this is actually bounded by some constant times. So remember there is s into s plus 1 below. So that will become some order of t square. So this will become this, because s into s plus 1 will become order of t square and this will become order of t to the power eta minus 2. Now you choose eta between 0 and 1. This will be integrable and the integral will be become something like this will, a will become b, some other constant time this. Now eta is between 0 and 1, you take limit t goes to infinity, this thing will become 0. So what we have proved is integrating along this line is same as integrating along this line. This is, we are doing this because we want to somehow wrap around this point, because we know it has a pole here and we know its residue is exactly what we want. So we want to wrap around this point, and that's what we will exactly do. Now we will consider this control. This is gamma of delta t, say. So fix t and choose delta small enough such that, so this is 1 minus it minus delta. So choose delta small enough such that there is no 0 here, and that can be done because zeros doesn't have limit points. So you can just choose delta small enough such that there is some gap between the zeros, and so you choose delta small enough such that there is no 0 in this region. Now you consider this integral. So integral of f along gamma delta t, and you have this the other integral, right? This is gamma of t. So you want to go anti-clockwise, right? So you want to go gamma t by 2 pi I fs ds minus, and to this, here you want to go in this direction and here you want to come back in this direction, minus we have this. So what is this? Here the integrals will cancel, here the integrals will cancel. So only differing region is this. And since the only 0 and pole in this region is s equal to 1, this integral will be just the residue. So this is x square by 2. And what is this? This is just psi 1x. So we have psi 1x is equal to x square by 2 plus 1 by 2 pi I we have this. We want to show limit of this divided by x square by 2 is 1. So we want to show limit of this can be this divided by x square by 2 can be made arbitrarily small. We divide the curve into 5 parts. We want to get an estimate of this integral. We don't want to exactly evaluate this one. So first along gamma 1, Let me get the estimates right. Okay. See, what you can do is, this is s plus 1 by s into s plus 1 by uh, minus zeta prime by zeta. So minus zeta prime by zeta, if you take t large enough, you can bound it by some constant time e to the power eta. Now this will become minus 2, this thing, and you will have a, and what is this? So this is real part of s equal to 1, right? Moving along this line, this is s equal to 1. So here this is just x square, because here s is 1. So this is just x square times this. You can bound this by this. So what happens is, uh, so you can write it like this, just x square by 2 times a. So this integral you can bound it by x square by 2 a times integral t to infinity, minus infinity to t, mod of t whole to the power eta minus 2. This thing converges. So this is some constant dependent on t, so which is just ct x square by 2. T is dependent on t, and t can be made arbitrarily small. This is minus t, sorry, minus t. T can be made arbitrarily large, so this constant can be made arbitrarily small. So we can write it like epsilon times x square by 2, where epsilon can be made arbitrarily small. Same goes for this one. It is just, you are taking modulus, it's just the same integral again, just for it will go from t to infinity instead of minus infinity to minus 3. So this shows this thing is bounded by something epsilon times x square by 2, where epsilon can be made arbitrarily small. What about the other three integrals? So integral along gamma 3. Here what is x to the power s plus 1? Just x to the power 1 plus delta 1 minus delta plus it. So it is just integral minus t 2 plus t x to the power 1 minus delta plus it I should write as goes from minus zeta prime by zeta. So what essentially you can show that it is actually less than x square minus delta, and in this region I'm not gonna go through all the bounds, because just evaluating integrals and this fs is bounded by x square by log x. You have to get some similar bounds. So you have to just do something similar to how we did in gamma 1. Just evaluate the integrals, use this property, and then somehow bound this value, and then bound the integral. Is essentially the same task. So you can bound this something like this. Mod of this thing, this is less than equal to epsilon times x square by 2 along this and along this, plus some constant which depends on t, doesn't matter, times x to the power 2 minus delta plus some constant which also depends on t, x square by log x. I wrote it x square by log x. So there. Now you just take this x squared by 2 minus 1. This will become epsilon. This will become this times x to the power minus lambda minus delta, and this will become 1 by log. Now take x goes to infinity. This will go to 0. This will go to 0, and this will be epsilon. Epsilon can be made arbitrarily small. So this essentially proves the prime number theorem. The second part is messy a little bit, but what essentially the crux of this thing is, uh, see, number theory is something pretty discrete. So when things like this came up, like how to get complex analysis into number theory, that is something that was not at all expected by people, because nobody thought of bringing complex analysis in. Analysis and number theory doesn't make sense usually, because you're just summing up numbers and stuff like that, and finding properties about numbers which are just integers, they're discrete, there is nothing continuous about them, and still you are somehow, you are, this analytic continuous is that's so powerful, because you have something discrete, you are able to convert it into something that is continuous, something that is in the whole complex plane. And once you have some properties in the complex numbers, it is really useful. So the complex holomorphism and stuff like that are very powerful stuff. So you can exploit them easily, and you can get some really nice results. So the main thing is this: how Riemann came up with the analytic continuation and zeta function and stuff like that, because prime number theorem was not very difficult to prove after that. I think Riemann came up with this stuff in 1950s, and then Hadamard proved this in 1990, in 1850s, and Hadamard proved it in 1990, 1892 or something like that. So it didn't take a lot of time to prove prime number theorem once we had this bridge between number theory and complex analysis. So, and Hadamard actually said that Riemann made a lot of conjectures about the Riemann zeta function, and Hadamard said that he could prove everything that was written in Riemann's notes except one. So thank you. References. Okay. So this book is from a complex analysis book. So I'll cite that one first. Complex analysis by Stein and Sakarsi. Very well-known book. It is actually lectures given by Stein in Princeton, and Sakarsi was one of his students. They later on, I think, wrote this book. So this is Stein and Sakarsi. Complex analysis is really good book, especially if you are interested in number theory. It has proofs of prime number theorem, and later on it goes into elliptic curves, L functions, and stuff like that. So it gives motivation to number theory, these books. And there is classic Apostle, Introduction to Analytic Number Theory, I think, Tom Apostle. And also for the first years, those who don't have a lot of background in number theory, you can try this one. This one is available in the library, in our library. I have read it from there only during my first year. So wait, Jeffrey Stoppel. So this is very basic, and it doesn't assume anything, doesn't assume integrals, doesn't assume complex analysis, and it is mostly a problem solving approach. It will ask you to guess some stuff about a sequence, then prove it, and then after you prove it, it will give this as a theorem. So a lot of stuff will come up as a theorem, and it will give something related to the average order of, say, divisor function, sigma function, and stuff like that. And there are some really nice stuff in this book. So it is pretty basic, and I think a primer. I might have, the words are the same, these are the main words, but I don't know, I don't remember the exact name of the book. A primer into analytic number theory, I think. So
Does anyone have any doubts?
what is the value of zeta of 0? Zeta of 0. I don't know specific values, but yeah, you can evaluate it in a sense. See, it doesn't make sense when you write it in terms of sum. It will become just 1 plus 1 plus 1. But essentially, you can evaluate it. You have to just evaluate the expression for eta. You get something in terms of the pi also. There will be pi of minus h by 2, pi of h by 2 gamma. So you'll have to evaluate this. So you have to find the residue here, and then write it in terms of, I don't remember specific values, but yeah, you can essentially find it. And zeta of minus 1 is minus 1 by 12. You can prove that also. It is just value of this expression. It is not value of summation 1 by n to the power minus 1. It is not summation 1 plus 1, 1 plus 2 plus 3. It is the value of this expression evaluated at minus 1. It happens this expression agrees with that expression at s bigger than 1, real part of s bigger than 1. So
Let's thank the lecturer once again. Thank you for coming to the talk.